Hello medical students. In this video we will finish up our first chapter of our MCAT prep course by talking about some topics involving force and Newton's laws of motion. And we'll begin with force and free body diagrams. And the first topic here is the so-called four forces of nature. And this is a very common way of describing the forces of nature. It's maybe not the most accurate possible way to describe them, but if you go by the book will list for you four forces. And so the first one is the strong nuclear force. And the weak nuclear force. And then electromagnetism, and then gravity. Now, the book then proceeds to explain how the nuclear forces are not so relevant to us. Now, of course, the nuclear forces are relevant in a medical setting. I mean, you have all kinds of medical imaging and treatment related topics that involve the nuclear forces. You know, you may have even heard of nuclear medicine. I mean, one obvious thing is radiation treatment or, you know, various imaging techniques. But in terms of working out mechanical problems, like these, you know, free body diagrams we're going to talk about, the nuclear forces are not going to show up in this context. So these don't show up for us in practical mechanics, in mechanical contexts. So we're focusing on these two. Now, electromagnetism manifests itself in a variety of ways, and the book will explain to you, let me draw a little line across here. The book will explain to you that most of the forces that you're used to experiencing, well, really all of the forces that you think of as forces in ordinary life, besides the gravitational interaction, are electromagnetic in nature. And the distinction that they make is they say, well, electromagnetism often manifests itself as what they call contact forces. And the story that they will tell you is if you press on something, like I press my fingers on the board, then what is actually exerting the force there is the molecules at the tips of my fingers are interacting electromagnetically with the molecules in the board. And so that's what's resisting. It's actually close range electromagnetic forces. But that interaction is very complicated because you have the individual electrons and protons of these atoms that are, you know, interacting in complicated ways. And it's very many instances, you know, billions and billions of instances of individual little electromagnetic forces that are pushing. So it's easiest to view that in a different way, as an essentially different type of force. And so you kind of, then you would put 3A here, which would be contact forces. And then you lump most of the forces which are actually electromagnetic in nature into this contact forces, because the only ones that are left out is like if you know, for instance, if it's a cold day where it's not very humid, down here, which is not very common in Mississippi, you get static electricity. And if you get your hand close to something, you can feel like the hairs on the back of your hand or maybe on your head or something standing up. That's a direct static force. That's a static electricity type force. That's a direct electromagnetic force. That's not a contact force because you're not touching the thing that's exerting the force on you. But other than that, most of the forces you think about, when you're lifting and moving and things like that, involve contact between objects. And those are essentially electromagnetic forces. That's what they boil down to. Now, I should say about gravity, well, I will say whether I should say it or not, that this is not really a force in the sense of something that pushes or pulls on things. And but you think of it that way, and this is really Einstein's understanding in the context of what's called relativity, that gravity is not really a force. It's if you want to be sophisticated about it, it's a structural aspect of the universe that involves the curvature of space-time. That's how you describe it in relativity. But we think of it as a force, and throughout this whole thing, we can always think of it as a force and never have to worry about it. But, that's a detail, so I'll give 30 seconds to that detail. So what all this boils down to, as the book describes, so all this just boils down to three forces, for practical purposes. One is like static electricity. So this would be electromagnetic, let me spell this correctly, electromagnetic, contact, which of course we know is really electromagnetic, but we're separating it, and then gravity. And so this together makes our practical list of forces. And henceforth, throughout our subsequent discussions, it will suffice to think about forces in this way. Okay, so we've talked about this and we've talked about this. Now let's move on to the important practical topic of free body diagrams. So let me copy this up here. Free body diagrams. And so what the idea is to isolate the relevant forces acting on the, I'll put this in quotes, interesting part of a system. Now there's some descriptive words in here, relevant forces and interesting part, and I have to tell you more about what those mean. So it's completely determined by what problem you're trying to solve and what aspects of that problem will let you solve the problem. Here I've drawn a picture of a block sliding down an inclined plane. And it will turn out that some of the forces that you see diagrammed in here will have a practical effect on the motion of the block, and some of them won't. And over here is the free body diagram, which simplifies this diagram to show a much more, much simpler diagram that has fewer components to it. And those are the only components that will actually affect the motion of the block. You recall from the 5-step method that was suggested at the beginning of the book that it had this, breathe and then dive, D-I-V-E, where the D stood for diagram, the I stood for isolate, the V stood for variables, and the E stood for equations. So where the free body diagram comes in here, you see this word isolate? That's exactly this word here. See this word diagram? That's exactly this word here. So it's at this point in your problem-solving process that you're thinking about making a free body diagram. And the point of it, so the objective of all this is to focus on what you need to solve mechanical problems. And just as important, and so I'll put it in quotes, and, I mean not quotes, caps, nothing else. So the sense in which this word free, the sense in which the word is free, is you're essentially taking the thing you're worrying about the motion of, and you're thinking of that as sort of the center of your universe. Here I've taken this little block here and I've just replaced it with a point, and the motion of that point is all I care about. It's kind of similar to when I had the hammer and I threw the hammer and I said, well, all you care about is the center of mass. If you were drawing a free body diagram for the motion of that hammer, what you would do, you wouldn't try to draw a complicated hammer. You would just take the center of mass and you would show what the forces on the center of the mass was. In that case, there was only one. It was the gravitational force going downward. So you can think of, here I've written in quotes here, free of clutter. That's a sort of another way of thinking about this word free, is that you have just removed all the stuff that will only distract you and that you won't actually need to solve the problem. So I've used up all my space here, so I'm going to erase this, and we're going to look in a little more detail at a specific type of free body diagram which involves inclined planes. And of course the book resumes talking about inclined planes a little bit later, but this is a good example of a free body diagram, and so we will discuss it now. So here's, this is an example, it's a good example. And this is a block on a plane. Now, it's possible, if you haven't seen problems like this before, that it's not absolutely clear and obvious what this means. You're supposed to be looking at this thing from the side, so let me redraw this. So what this is this is sort of like a wedge-shaped or ramp-shaped plane. And so the point is the plane is here, and then the rest of this is whatever is supporting the plane. So this could be, you could imagine having like a block that's an inclined plane like this, and then having a little car that rolls down the plane or something like that. But in this case, we're going to simplify matters, and we're just going to take a block. In this case, it's going to be a rectangular block. And we're going to say the mass of this block is m. We're just going to call it m. And so the idea, of course, is that you expect, provided that the incline of the plane is sufficiently high and the surface of it's not too rough, you expect the block to want to slide down the plane. And the question is going to be, well, how fast will it slide down the plane? And this will depend on a number of factors. Now, what's going to end up happening is the motion of the block will be determined by the forces acting on the block. And this is kind of putting the cart before the horse in the sense that we haven't yet officially talked about Newton's laws of motion. But I'll skip ahead just over here and say that what's going to end up happening is the net force, that's this F, on the block is going to determine the acceleration of the block by this equation, force equals mass times acceleration, and that's a common expression of Newton's second law of motion. But in order to apply this, we have to figure out what the forces are, and as we see later, it's going to be the net force that matters. To find the net force, it is reasonable to begin by discussing what all the forces are. So one of the forces is a force due to gravity, and this is a force that's going to point straight downward. And the size of this force, in this case, is going to be mg. Now, usually we'll decide that the upward direction is the positive direction, and so this would mean in terms of, say, so e.g., if you have, say the mass is 5 kilograms. If m is 5 kilograms, then this force, mg, will mean it's the 5 kilograms, and then it's times minus 10. I guess I should go ahead and put my units in here. So this would be 5 kilograms, and then it would be a minus 10 because it's going downward, meters per second squared. And, so this comes out to minus 50, and then the kilogram meters per second squared is what's called newtons. That's an abbreviation for that. So you've got that force, which is just abbreviated with this mg. Now, this force here can be split up into two parts. One is the part that is pulling it down the plane, and it turns out that the size of this will be mg sine theta. And then the other part is the part that's pushing it down into the plane. And so that would be, I don't know where I'm going to draw it here. This would be mg cosine theta. Now, as a result of Newton's third law, which we'll talk about in a second, the plane will push back up on the mass with a equal and opposite force, which will be mg cosine theta, and that's why I've drawn the mg cosine theta here. Now, the reason you know that is because if there was a net force either in the direction of the plane or away from the direction of the plane, then that would make the mass move. But since the mass stays on the plane, you know that whatever this force is has to cancel whatever this force is. And if you wanted to, you could put a minus sign in front of one of these, one or the other. Here I've just used the arrows to say that this force is canceling out this force. This one's pointing this way, this one's pointing this way. And then there's also going to be a force of friction in a realistic situation. I've called this F, and then this little letter down here, this is mu. This is Greek, the Greek letter, and it's called mu, and so it's like an M. So it's like an M. I don't know. It's like a very distorted M, I guess. It's more like a capital M, I guess. It looks more like that, like a capital M. But that's what it is. That's what that funny letter is. And that's often used to represent friction. And so what the friction force will do is it will always resist the motion of the block. So this, now in this case I've drawn the friction force as being less. I've made this arrow shorter, so I've drawn the friction force as being less than what the mg sine theta is. And if that's the case, then the block will slide down the plane because this force here is bigger. So this is, in this case, this is all the forces in this particular situation. Of course, you could say, well, there's also gravitational force from the moon. And forces from the moon and the sun and stuff are not irrelevant on Earth. I mean, you know how the tides are related to the force of the moon. But we're not taking into account things like this, or that a wind is blowing on the block or anything. These are the forces that we're taking into account. Now, it turns out that, and I should point out, just for clarity, this, maybe I should actually draw a little dash line here for this force and this force here, because this force and this force are not independent additional forces from this mg here. They are components of the mg. So it's not like you have an mg sine theta and mg cosine theta and then an additional mg. This is just a way of breaking up this total mg force here. So really, just this one, and this one are independent. And these two are just a convenient way of breaking up this one because it breaks it up into a component that's going to go down the plane, and that's the force that's actually going to be relevant in terms of what the motion is. Now, all of this is messy. And so this is sort of a prototypical sort of non-free body diagram because it draws a bunch of irrelevant stuff. And of course, you could draw more irrelevant stuff. I could have the surface on which the plane is sitting there. And I could have, I can draw any number of things in here. I can just put artistic features in here with, shading, or I can put dots in here. Any of this kind of stuff, like some of the pictures the book draws, they have a bunch of boxes sitting over in the corner. They have, all these sort of details that don't have anything to do with what's actually happening in terms of the physical problem that you want to solve. So the way that the free body diagram for this is going to look, and there's different diagrams you could draw and call them free body diagrams. The one I'm going to draw is actually the simplest in the sense that it only takes into account the forces that are going to ultimately determine what the motion is. And so this is just a reprise of what that little diagram I drew over there is. I'm not going to draw the plane at all because I don't care about the motion of the plane. The plane's not going to move in this thing. So I don't even worry about that. I'm not going to draw the surface. All I'm going to draw is something representing the block. Now, I don't care about the whole block. I don't care what its shape is. I don't care what its size is. I don't care about anything except for just a single point, which I'll draw at the center of mass of the block. So I'm just going to draw this here. So now this is commentary. So this isn't the free body diagram, but this is single point at the center of mass of the block. I don't worry about the shape of the block or the size of the block or any of that. Now I'm also not going to draw this mg cosine theta cancels this mg cosine theta. That's the action-reaction thing that we'll talk about in a minute. For every action, there's an equal and opposite reaction. The block presses down on the plane, or this way on the plane. The plane presses back up on the block. I'm not going to draw those because they cancel. Now, remember, this and this were the components of this mg. So I wouldn't have to draw the mg. If I drew the components of mg, that would be fine, but I don't have to draw this component because it cancels this component. So all that's left is this component, which I've drawn a little bit longer. So this is mg sine theta, and the friction force, F mu. I don't really want, this is the same force as before, so I guess I should draw it to where it looks like the same length. And so, other forces, let me draw more commentary in here. So this is, other forces cancel. Now you could tell me, you could object and you could say, well, these forces partially cancel too. This one points this direction with some magnitude, and then this cancels part of it, and you'd be absolutely right. You could draw something that would be even simpler, which would look like this, and it would just be the force mg sine theta minus the force due to friction. And that would also be a free body diagram. If you want to, you could put m here just to represent the mass, if you wanted to. Now, you could be a little bit less simple to start with, and you could draw all of those forces on here if you wanted to. And you could say you could have this one, and this one, and this one, and that one, and that one. And you could label them all. And that doesn't look quite accurate. You could label them all, and then you could draw a simplified diagram in which some of those cancel. So there's choices in terms of how to draw the free body diagram, but what the moral of all this is, if I have room to write down here. So moral is to just draw it so as to simplify the problem. So draw the free body diagram to simplify. Now, if you're not sure what cancels out at first, then maybe you draw all the forces in there, and that's fine. But then you can maybe see, once you've drawn it, I could see, okay, well, that cancels that. I can take those two out. And then I take out that one, and I'm further along because I have a more simplified diagram. And then, of course, I'd be taking that one out too, because that one was a component of that one. Anyway, so this is the idea of free body diagrams, and we'll see more of these sorts of things.